Good morning. This is Lecture 4 of Measurement Science, Wednesday, 20 November 2013, for the University of Twente in the Netherlands. This is Ed Garland giving the lectures for Measurement Science this year from the University of Tsukuba in Japan. Pay attention to Blackboard and your syllabus. Homework number 4 will be available on Blackboard today that you can download and start doing the exercises. And homework number 2 is due today, using the same rules that have been discussed in the previous lecture. Today the lecture will have two primary focuses. The first one is physical principles of sensing. We'll look at different types of sensors and physical effects that we can detect with these types of sensors. And then the second part of the lecture will look at modeling physical domains and then applying those using thermodynamics and the theory of two-port networks to try to make a more physical-based description of a particular sensor. I have included in an appendix examples of mechanical, thermal, and hydraulic system modeling of these particular domains. I won't go over it in the lecture today, but you can go over it in the appendix. We will see these later in the lectures, so it will be helpful to be able to have this knowledge before we go into the lectures next time, because we have concepts from the mechanical domain, the thermal domain, and the hydraulic domain about making comparisons or analogs to electrical circuit analysis. And this will be helpful later in the course. In this lecture, I'm going to talk about capacitive, resistive, and magnetic principles of sensing, the Hall effect principle, piezoelectric and piezoresistive principles, and their application for strain gauges. Capacitive sensors usually consist of two parallel metal plates in which a dielectric between the plates is either in air or some other medium that can be polarized. For a parallel plate capacitor, we've seen this relationship where we have the relative permittivity, the permittivity of free space, multiplied by the area overlap of the plates divided by the separation distance. So the capacitance is a measure of the amount of electrical charge stored, or basically separated by distance d for a given potential phi sub e. So in this lecture, pay close attention because I have used phi for electrostatic potential and a capital phi for magnetic flux. So pay attention to the symbol with relationship to which physical domain we're talking about. And then there are 5 relationships for the capacitor. We have on the left the capacitance is equal to the electronic charge divided by the voltage, which is essentially Gauss's law of electrostatics, and the capacitance formula. And then we have the integral and the derivative, the differential form of the potential and the current with respect to the differential in time, and then the stored energy in the capacitor. So there are different types of capacitive sensors that we will be considering in this lecture and the course. We have single plates where one of the plates is moving, or both of them, they can be moving, and the net separation distance, delta D, then gets reflected in a capacitance change that you see in the equation below the left figure. Right is a differential vertical displacement where usually the center plate, which is gray, is moving, and then the upper capacitance increases and the lower capacitance decreases. And then you can calculate the delta C separately between those two. Lateral displacement is one of the plates is moving in the lateral direction, delta x, and the corresponding capacitance changes, and you see on the equation under the figure on the left. And then we also have a differential lateral displacement capacitive sensor where the overlap between the two plates is changing now with respect to delta x. And in this case, B is the overlap distance this would be in the y direction, and d is a constant separation distance. When delta x is equal to 0, then the change in capacitance, or the difference in capacitance, is going to be 0. That means C1 is equal to C2. There are also comb finger capacitors, and you can see on the picture on the left that the overlap capacitance is dependent on basically these fingers that represent plates, and we ignore the end capacitance there, which is called CP, which is the parasitic capacitance. And you can look at this on your own to derive this change in capacitance delta C. And remember here, N is the number of fingers that you have. Now, I'll show an example in a minute about why this is important. These comb finger capacitors can be made using microfabrication techniques, and most of the accelerometers that are in cars today are based on these comb finger capacitors, which are moving structures. Let's do an example of reading out the capacitance of one of these capacitive base sensors using a capacitive readout circuit that's showed on the left-hand side of this slide. In this case, we will work on a lateral displacement differential capacitance sensor, which is located on the left of the circuit diagram. And on the right, we have a charge integrating amplifier with voltage output. The positive terminal is connected to ground, therefore the negative terminal is a virtual ground. We have an RC network in the feedback path between the negative terminal and the output terminal. This general type of capacitive readout is quite important. It will appear on at least one of the homework assignments, and definitely on the final exam. So I recommend to practice solving these types of problems and to remember them for the exam, because you will see this multiple times. So to solve this type of problem, the first thing that we do is we calculate the differential capacitance, delta C. And I've defined delta C as capacitance C2 minus capacitance C1. And when we don't have a delta X shift or movement, therefore delta X is equal to 0, then C1 is equal to C2, which is equal to the permittivities times the lateral plate dimensions AB divided by the plate separation distance. When we get a delta X movement, C1 decreases by a factor of delta X, and C2 increases by a factor of delta X. Therefore, the delta C that we get is 2 times the permittivities times B times delta X, the shift, divided by plate separation. Now, to analyze this type of configuration with the amplifier readout circuit, we're going to perform Kirchhoff current law at the negative terminal, which I've labeled as V minus. So if we sum all of the currents at that node, V minus minus VI over the impedance of capacitor C1, plus V minus minus VI over the impedance of capacitor C2, plus V minus minus VO over the impedance of the feedback network. And all of those currents summed should equal 0. The feedback impedance is RF divided by 1 plus j omega RF CF. And if we choose j omega RF CF much greater than 1, then we can simplify this impedance to 1 over j omega CF. And then our V out is equal to Vn delta C over CF, which is equal to Vn times delta C over CF. And then V out is equal to Vi times delta X over CF times 2, the permittivities, times B divided by D. So the transfer function of this system is V out over delta X, which is equal to Vi over CF times 2 times the permittivities times B divided by D. So remember how to analyze this and the assumptions that were made with the feedback capacitors and resistor, or the impedance of the feedback network, in order to simplify the expression. And then once you have this expression, maybe you will have to put in some values to see what kind of displacements you can resolve with this type of sensor. Now, as I said earlier, the capacitive sensor is extremely important, and it's used in many of the modern miniaturized acceleration and gyroscopes that measure other properties for guiding airplanes and these types of things. So these miniaturized sensors are based on comb finger capacitors that move when mechanical structures move with these change in acceleration, etc. The bottom left-hand picture is a picture of one of these comb finger capacitors that has thousands of these interconnected fingers to give really high overall capacitance overlap values. And amazingly, you can buy this accelerometer for a few euro. This is an old picture from Analog Devices. And amazingly, if you configure these in the right way, the right really precise readout mechanism, you can resolve movements in the comb fingers on the order of picometers, about 100 picometers. And remember that that is 10 to the minus 12 meters. And remember atomic distances on the order of angstroms, which is 10 to the minus 10 meters. So for a few euro, you can resolve displacements of those capacitance fingers that are smaller than atomic distances. Quite a powerful technique. Next, we have resistive sensors. These are electrical resistive sensors, and they rely on the resistance of a material when a measured variable is applied to it. These are most commonly applied in temperature sensors, using resistance thermometers or thermistors, or in the measurement of strain, piezoresistive properties of materials. Now, the resistance depends on the material and geometry. Specific resistivity, which we've given as ρ, is related to the electric field, and the flux, which is the current density, and which can be expressed as a mean time between collisions, tau, charge, electron mass, and the number of electrons per unit volume in the system. These are usually for metals. So semiconductors, typically we don't use this simplified form for the resistivity or the conductivity of the material. And then resistance with unit ohm then can be multiplied by the resistivity multiplied by the length of the material divided by the cross-sectional area in which the current flows. And then just Ohm's law, the voltage, which we've given phi sub E is equal to I times R. For temperature sensors, typically we use metals that have a somewhat linear response to increases or decreases in temperature. And when we do that, then we can expand this in a first order polynomial, which is essentially R as a function of temperature then is your base resistance R0 at the characterization temperature, or room temperature for example, plus alpha, which is the temperature of coefficient of resistance, and then T minus T0. And T is then the temperature variation increases or decreases. And this is assuming that this response is linear. If you have a nonlinear response, then you have to use more terms to represent the curvature in that response. Now, magnetic sensors, we'll talk about three types today. Inductive sensors that translate movement into change in the mutual inductance between magnetically coupled parts. A variable reluctance sensor. A coil is wound on a permanent magnet, or a magnetic core, which can be iron or some other material. And an eddy current sensor, which consists of a probe containing a coil that is excited at high frequencies, and then another material that interacts with the magnetic induction or the B field that modifies the flux in the end that gets represented in the current through the coil. And we'll talk a little bit about that. So magnetics, then we have to come back to Maxwell's equations. And if you recall in your electromagnetics fields course, that typically the constitutive equations that relate the magnetic field strength to the magnetic induction in the microscopic Maxwell's equations, there's also a term, capital M, which is the magnetization. And likewise, for the dielectric displacement, it also has an additional term for polarization of the material. If you're working in free space, then typically these are ignored. If you're working in a material that has particular properties that will affect both the magnetic field strength and dielectric displacement, then you have to include these as your material properties. So the different types of magnetic induction, or I'll call them the B fields from now on, just to make it a little more simplified. And we see 5 different B field configurations. We have the B field around a magnet, around the poles. Then we have a coil, flowing current through the coil I, which generates a B field. And you'll see that they always terminate, they always terminate on themselves. So remember that the divergence of the B field is equal to 0. Then if we have a magnetic material, such as iron, and we wind a coil around this, then the coil is going to generate a B field in the material, or a magnetic flux, which is basically, the magnetic flux is the integral of B dot dA, which is the area, the cross-sectional area. So this represents the flux. And then in D, if we have just a simple wire and we flow current through it, then we get this loop, this B loop around the coil. If we have other coil shapes, then we can generate the B field with different types of geometries. So in magnetic circuits, these are primarily applied to actuators and motors. The most important property is inductance, L, and Faraday's induction law states that the induced voltage, which is called the electromotive force, or EMF, is equal to the rate change of the magnetic flux, which is the capital phi sub B. And then the electromotive electrostatic or electromotive force, this voltage, is phi EMF. So when we do self-inductance, this is a simple coil without any magnetic material, then the EMF voltage is going to be equal to the negative differential of the flux times the number of winds in the coil divided by the differential of time. And that's equal to minus L di dt for N phi B equal Li. And N phi B, which is the flux linkage, is equal to this Li. And this is quite important. So this L times the current is really the flux linkage. How the flux from the coil gets linked into this, the B field, okay, and it gives you the voltage. And then we have the energy stored in the self-inductance as well. Now the mutual inductance is for two coils that are placed in very close vicinity. One coil induces EMF in the second coil. So then we have the induced EMF is equal to this coupling coefficient, which is, you'll play with this with transformers and these types of things in your practicum, and that's equal to the di1 dt. And these are two examples of using this mutual inductance. We have two coils, one outside the other coil, and then inside the mutual inductance is going to be this cross-sectional area, and then the multiplication of the two turns, N for the inner and capital N for the outer. And then the other mutual inductance is if you have a magnetic material and you're going to drive this with, let's say, N1, and you're going to read out with N2. So the mutual inductance between these is going to be N1, N2, H, which is the height, divided by 2 pi natural log B over A, which is the difference in the radii of the magnetic material. Those are two examples of circuits. Now, these can be used for transformers. This is an example of a half of a transformer circuit where we drive a current through the coil on the upper left-hand picture, and it has winding has N turns. And in this case, this electromotive force is lambda, but this is just an old picture taken from a book, so this is still our electromotive force across the coil. And you see that we have a magnetic material, we call it a magnetic core, the magnetic flux lines, which is basically the B field, but then the flux is the B times A, essentially. And the cross-sectional area of the magnetic core, the mean length, and we have the magnetic core has a particular permeability. And we can construct a lumped model of this now, the electromotive force F, the magnetic flux phi sub c, and then a reluctance, which is a magnetic equivalent of electrical resistance. And then we can derive using Ampere's law the basic properties which are similar to Ohm's law. So then the magnetic flux in the end in this very simplified system is going to be then the magnetomotive force divided by the reluctance. And we can use this to design magnetic circuits, these basic laws. And then if we have an air gap, then we can also include this into our calculation, so we can then make a lumped circuit that consists of a reluctance for the core and then a reluctance for the air gap. And remember the permeability in the air gap, then we assume just mu sub 0, the permittivity of free space. Now different types of magnetic sensors, the measure ends, remember magnetic field strength, magnetic induction, and these are typically direction sensitive vectors. So displacement sensors, we show 4 on here. We have a magnet that creates a B field, and then we have a B sensor, some sort of B sensor, that is going to modify the readout of the B field as the displacement variable x is changed. So the output of the B sensor is going to change as a function of your displacement between the sensor and the magnet. We have an induction type of sensor where we have a loop and we measure the induction voltage or the voltage induced on the loop. And in this case, this voltage induced is dependent on how the magnetic flux changes with time. So this is really a velocity sensor. So if you have a B field that's generated by the magnet in this case, the voltage that is induced on these output terminals of the coil on the second from the top image, then as this loop is moved in time, then the voltage is going to be a derivative of essentially dx dt. Inductive displacement sensor, which is the third one on the list, and we have essentially the case where we have either one coil L1 or two coils L1, L2, and then we have a core, and the amount of overlap between the core and the coil is going to give us a function of displacement, because remember that the current that we generate is going to be dependent on the core inside the loop that you have. So then L, the linkage is going to be then a function of the displacement x. And then a transformer type where it's based on a very similar principle where the voltage overlap is going to be dependent on the magnetic material between the core, and then our Vs, which is our signal, over Vp, which is a primary coil, is going to be a function of the displacement x. And you will get much more experience in the practicum in playing around with these types of sensors. So the displacement sensing magnetic fields, as I said earlier, two types of sensors that we'll talk about today: a Hall sensor and a magnetoresistive type of sensor that can be used for this type of displacement sensing. Now the inductive sensors, you can have two types of sensors. I show two here. One is a magnet, one is an electromagnet. And in this case, as I said earlier, the voltage induced at the output of this coil is a time derivative of the flux, so this is really measuring velocity of the coil as it's moving. And the same general rules apply to also the electromagnet that's on the bottom. So the coil is moving and we can measure the velocity of that coil by the B field that's being modified. And these induction sensors, they are ubiquitous. They're used in many, many places. They can be really inexpensive. This is an example of an E-shaped ferromagnetic body. So the permeability, the material, the E-shaped material will support a magnetic flux in it. And it's excited with an AC current. The displacement is to be measured as this other ferromagnetic plate comes in close proximity. So when you have these two ferromagnetic materials, when the displacement, the T-shaped material is far away, then the B field that is induced in this material will have a certain configuration. As this T-shaped material is moved closer and the gap is reduced, then the entire circuit changes, and the induced current that you apply or you measure is going to change. So you're just changing how the B field forms in a new geometry, and it causes the flux pattern to change. And then we can measure these. Now the other displacement sensor is an eddy current sensor. So normally if we have this electromagnetic configuration, electromagnet configuration, which generates a B field, if we put some target material in the path of the B field, okay, this is going to modify the current. Now, a couple of things will happen. in this material, depending on the conductivity sigma and the permeability, so whether it's a highly conductive material or it's a material that is ferromagnetic, it can support a magnetic flux, we will generate eddy currents. Now, eddy currents in general are not good because they heat and they damp mechanical systems, moving systems, but they're interesting for displacement sensing. So there are two things that happen, two physical effects. We get eddy currents, which are due to the material conductivity, and we get a reluctance change in the magnetic circuit. Because now if we put a material that has a certain permeability, it will modify the B field, because now you have a new magnetic circuit, and these are opposing effects on the sensor output. Now remember that our magnetic field strength gets modified in this case because we have the magnetization of the material. Okay? So if we have a conducting target material, which means we have a high sigma, and we have our permeability is 1, then as x, the displacement between the target and the sensor, is reduced, then our induced current is going to increase, and then the counter fields due to the target are going to increase, which means that the B field, the original B field, is going to decrease, and then both the flux linkage and the magnetic flux are going to decrease. Okay, that's one thing. Now the other thing is that if we put a target that has a ferromagnetic material, which is typically the conductivity is not as high, but the permeability is larger, then as X decreases, then the reluctance of the magnetic circuit is going to decrease, and then the flux linkage then will increase, and if the flux linkage increases, then our signal increases. So this is really how we want to optimize this sensor, by using a ferromagnetic material. And then we have some sensitivity curves located on the bottom. So if we so if we increase the permeability, then the flux linkage is going to increase. If we decrease the resistivity, okay, then also we will decrease the flux linkage, and this means also increasing the conductivity. So we want low conductivity and high permeability, so that the readout signal that we get increases with a closer distance. Now, variable reluctance sensors, essentially we're going to be dealing with the same type of basic properties. We have a coil that generates a B field, and then we put some type of ferromagnetic material that can support magnetic flux in the system, or it's going to modify the B field in the system. And in this case, we put this rotating wheel, and as the air gap between the tooth of the wheel on the left-hand side is small with respect to the tooth on the pickup coil, then the reluctance is going to change a certain amount. Then when we're in the non-tooth region of the rotating wheel, then you're going to get a variable signal, current signal the induced current signal that you have on your system, or actually the voltage that you induce at the terminals of the coil is going to change respectively with the air gap changing, getting smaller, larger, smaller, larger. Hall effect sensors, quite an important type of sensor for many different types of applications, and it requires the application of a B field, but how we interpret this is a little bit different. The picture on the top shows a material which is a green-blue color, height D, lateral dimension B, and it supports an electrical current, I, so we're flowing current through this, and which means that we have electric charge, So the current is equal to dq dt. So we have charge that's flowing through the system. And in this case, we apply a magnetic field perpendicular to the material. And you can see the red arrows indicating the direction of the magnetic induction. And what this does is this applies a force on the moving charges, and this is called the Lorentz force. And we calculate that by Fl is equal to Q times V, which is the velocity of the carriers, cross the magnetic induction. And the charge displacement, which gives you an electric field, which gives you an electrostatic force, and we get an equilibrium where the Lorentz force is equal to the force that we place on the charge displacement. So essentially what happens is we basically apply a force to the carriers and we push them to one side of material, which generates this Hall voltage. So essentially, if we have charge carriers, and let's say that they're somewhat uniformly distributed, when we don't have the magnetic field, when we apply the magnetic field, we push them to one side and we create a potential called the Hall potential across this structure. And then we can calculate this Hall potential by being 1 over NQ multiplied by the magnetic induction divided by the thickness of the material, which is then reformulated into the Hall resistance times the current times the applied B divided by the thickness of the material. These are used in many different types of applications in both 2 dimensions and 3 dimensions. Very important application is doing mobility measurements in different types of materials, where you can, with a series of experiments in different types of Hall structures, where you generate this Hall potential across the material by the application of magnetic induction, you can characterize the mobility of the electrons in the holes. And this is used quite extensively in the semiconductor industry and in other industries as well, basic science as well, characterizing materials. Piezoelectric sensors, these piezo means to change. So the piezo, we have an electrical change in the material, produces an output voltage when a force is applied to them. These are used for ultrasonic receivers and also as displacement transducers. You can use them for measuring acceleration, force, pressure. They're really widely used in industry, different applications. So a piezoelectric sensor, think of the material located as a blue block, which is some piezoelectric material, like quartz, for example, is a good material. And then we put 2 electrodes, 2 metal electrodes in the top and bottom face. If we apply a force to this material and we deform it, let's say in the x direction, then we will generate an electrical charge, and the electrical charge is proportional to the force that we apply. And then the voltage that gets generated between the 2 plates using Gauss's law then is simply that's divided by the capacitance, and therefore the voltage output from the capacitor is proportional to the applied force. Now the Q, the charge that's generated, is equal to some constant, material constant, multiplied by the force that we apply. And this material, this piezoelectric charge constants, Dij, can have different units. And these are really material properties. And the magnitude of the polarization effect, which is basically generating charge for a particular force, can be represented by a polarization vector. So remember that the material is three-dimensional. So then if it has three-dimensional properties, then you have to create these vectors, or actually these are tensors that represent how the charge is going to change depending on how a particular direction of the material is deformed. And if you have, and different materials will have then different polarization vectors. And you can see that we have 9 different coefficients to represent the different charge that can be generated depending on the material. Okay, so choosing the material that gives you a very simplified charge constant generation in a particular direction is quite important. So the voltage gradient along any particular direction is going to be G sub Mn, which is going to equal the charge constant divided by the permittivity of the material at that location. Now then we get a coupling coefficient. So this is one of these coupled systems, mechanical energy to electrical energy. Okay, and you can see gamma is the square root of dmn multiplied by hmn. And E is then the electric field of the system. In the x direction only, let's try to simplify things. The charge that's generated by a force that's applied in the x direction is equal to d11, for example, times Fx. And then the voltage generated across the capacitor, parallel plate capacitor, is going to be equal to d11 divided by the permittivities multiplied by the area overlap, and then that quantity multiplied by the applied force. The equivalent circuit diagram of the piezoelectric sensor is shown in this diagram, where we have the voltage generated by the piezoelectric sensor, which is represented by Q divided by CE, that is in series with an equivalent capacitor or capacitance of the piezoelectric sensor, because you have this parallel plate capacitor, and in series with an equivalent electrical resistance. The piezoelectric sensor readout uses again a charge integrating amplifier that has a feedback impedance network located between the negative terminal of the operational amplifier and the output terminal. On the left-hand side of the circuit, we have the equivalent circuit diagram of our sensor, and in the center portion of the circuit, we have the equivalent RC network of the coupling cables that are used to connect the sensor to the readout circuit. Now, in this connection, as we talked about earlier, the virtual ground at the negative terminal effectively shorts RC, CC, and RS. So we can, with reasonable accuracy, remove those from the circuit, which allows us to formulate a relatively simple transfer function, which is V out over the input voltage, which is Q over CE. And if we do some of the algebra, then the transfer function is equal to negative CE over CF multiplied by J omega RFCF over 1 plus J omega RFCF. Piezoresistive sensors to strain gauges, and we will have an example of like this on the exam, so please do pay attention to it. Piezo gauges are thin wires of films that are attached to a particular carry material. The wire or film can easily be stretched or strained. and an applied strain will cause an elongation to the length of the sensor. And then we can make some definitions here that the strain in this case is given the symbol sigma, so it's not conductivity in this case. It's equal to force over area. Okay, and then in the end, strain is equal to delta L over L. This is called the strain, and it doesn't unitless. So if we have a particular resistance, which is the resistivity multiplied by the length divided by the cross-sectional area, then the voltage that we get is A times L, and we can work through this particular these expressions, and we can see that the resistance at the end is going to be equal to 2 times the resistivity L over the voltage that you apply. Okay, very simple concept, that you have material and you're stretching it and you change the resistance, and then you want to use that delta L over L into a delta R over R, and then we do the sensing, much like we did in the lecture 3, where we were using a full bridge configuration with delta R plus and minus depending on how you strain the material. The sensitivity of a strain gauge is expressed in relative resistance per unit of strain, and it's called the gauge factor, and we saw this in lecture 3 as well. Delta R over R and delta L over L, and this is unitless. Now the piezo resistor sensors are typically made from semiconductor materials where we have a p-type region which has been diffused into an n-type base. The resistance of this varies greatly when the sensor is compressed or stressed, so you get plus or minus delta R. This is frequently used as a strain gauge where it produces significantly higher gauge factors than metal wires or metal foils, and it can be mass produced, so it can be relatively inexpensive. Now an example of this is these semiconductor resistors R1 and R2 are placed onto a diaphragm, which is basically a suspended plate. It can be rectangular or circular. When a pressure is applied, for example, to the top plate, it's going to deform the plate and push it down. And then the resistors are going to be elongated in either a longitudinal or transverse direction. And you'll see delta R over R of each one of these sensors. Then it's going to have components for resistance change in the longitudinal direction and the transverse direction, so X and Y directions. And then depending on the material, it will have different properties depending on whether you stretch it in the Y direction or stretch it in the X direction. And you can engineer these systems to give you particular type of resistance change depending on the strain that you apply to the material. And then you can calculate a V output voltage based on a V input voltage. That's just a material property. So you can really precisely engineer these. I won't go over this much more because in lecture, I believe, lecture 9, we will design one of these sensors, and I will explain what these parameters pi L, sigma L, pi L is a material property, and this is strain applied in the longitudinal direction, and then we have also a term for the transverse direction. So depending on the material and how this is engineered onto a membrane or some other type of bending structure, then we have to be careful how we formulate these equations. Now I'm going to show this again because I want you to remember this for the exam and for the homework. One of the most common readout techniques for piezoresistive is a bridge configuration, and I want you to be able to derive the output, the transfer function V out over V in for each one of the single element, half bridge, and full bridge configurations. Okay, that brings us to modeling physical domains. the last part of the lecture today. It's a little bit long because I give some background material. Um, but essentially, what I want to get in the remaining part of the lecture is to understand how a two-port network works, and we will do an example of a coupled system, electrical, mechanical coupled system using a piezoelectric sensor. And I want you to remember the general formulation of this. We do some thermodynamics and introduction to new types of concepts, but in the end I want you to remember the two-port network and how to manipulate the two-port network. So in modeling physical domains, we have two basic approaches: a black box model approach, where we saw in the second lecture modeling system dynamics using fixed model. These are first order and second order systems. And also the accelerometer in lecture 3. These are, you assume the system has a particular dynamic behavior, and then you use a partial differential equation, and it doesn't always have a physical meaning for all of the materials involved. Another approach is to use a two-port network, and this gives a more systematic approach that combines physical effects, limited, in coupled domains. Okay, and this is used widely for the modeling of integrated circuits for AC and DC models if you've had the semester course. This is where those models come from. Okay, so the two-port network, it has across and through variables. Sometimes these are called across and through, or effort and flow. These are the same. The across variables, EI and E out. The through or flow variables, FI and FO. Integrated circuit models, both, this is an example of an AC model. This is an AC model. This is a two-port network, and it has many capacitors, current sources, resistors, that essentially give you some physical meaning for the real integrated circuit, and then how it affects the output from the system. So you'll apply a gate voltage, and you're going to induce some AC current through this ID, and then how this AC behavior in frequency is affected by all the different capacitances. So in the semiconductor course, you will see these types of, or in the circuit analysis course, semiconductor devices, you will see these AC models. The origin is really a two-port network model. Now, the physical signal domains, sensors most often convert non-electrical effects into electrical signals. The conversion process can be direct or indirect. Examples of these are thermoelectric and piezoelectric. So we'll really go over the piezoelectric in depth in this course, so you get a better feeling for this. In coupled domains, a sensor performs an exchange of information in the form of energy from one form to another, and therefore operates at the interface between different physical domains. From energy considerations, a framework using the laws of thermodynamics must be used, and we will derive this basic process in this course. And we're going to consider electrical, magnetic, thermal, and mechanical domains in our description, but it's not limited to these. So from thermodynamics, that you probably learned in high school, we have 4 basic laws. Okay. The 0th law, the definition of temperature and the thermal equilibrium. The first law, conservation of energy. Now the second and third laws are due to what's called something called entropy. Okay. And this has to do with the characterization of the randomness of the system. This is concerned with spontaneous direction of processes determined by changes in the entropy. When two systems are brought into thermal contact, heat flows from one with a higher temperature. And the third law, all perfect materials have the same entropy at temperature equal to 0. At higher temperatures, the entropy increases. And another fact is that it's impossible to cool any system to absolute temperature 0. So the 4 laws are important, primarily the entropy, which tells something about the state of the system, which is a temperature, which is a function of temperature. Now the fundamental equation of thermodynamics is the internal energy of the system, which may include terms for different types of work. Involves only differentials of extensive variables and yields intensive variables as partial derivatives of the internal energy with respect to other extensive variables. In addition to the terms from the combined first and second laws for a system involving pressure-volume work, the fundamental equation for the internal energy may involve terms for chemical work, gravitational work, work of electric transport, elongation work, surface work, work of electric and magnetic polarization, and others. So the internal energy is really the temperature multiplied by the differential of the entropy, plus all these other work terms in the system that you have to have. So your real job is to determine what kind of work terms are important for your sensor system. Now, just a general definition, intensive variables, these are physical properties of the system that does not depend on the system size or the amount of material, for example, density. An extensive variable is a property that is directly proportional to the amount of material in the system, for example, mass. Mass of your system is dependent on the amount of material. Now, for these types of systems, we define types of work, okay, that are to be used in the internal energy, and something called conjugate pairs. So these are pairs of that give you different types of work that we consider. Okay, these essential work terms: pressure volume, elastic work, gravitational work, surface work, electric polarization. So here we have E and dP, magnetic polarization, B and M. Remember that we're dealing with materials. Tension deformation, stress and strain, electrical, magnetic, and then thermal, where sigma is our entropy. And then the rightmost column shows the differential work with respect to du. So the conjugate quantities that we use in this lecture, electrical, magnetic, thermal, and mechanical, are listed here as we've defined them in the table before this. So let's do an example. And the signal domains that we have are mechanical, which are stress and strain, T and S. Electrical, so then we deal with the field strength and the electric displacement. And thermal, we deal with temperature and entropy. For extensive variables, the internal energy changes like this, which is du is equal to theta times d sigma plus T ds plus E d capital D. Now for intensive variables, the internal changes as dg, which is the Gibbs free energy of the system. And then we use terms minus S dt, stress and strain and stress, minus d capital E, electric field, minus sigma d theta, which is the temperature. Okay, so we're going to move between intensive and extensive variables, and then we need to be able to go between these two forms of internal energy changes. Now, the first law of thermodynamics states that the internal energy of a system is constant unless it is changed by the work, W or Q of a system. Okay, and so if we review this then, our extensive variables that depend on the amount of material are S, D, the strain, electric displacement, and entropy, which is going to be, these are going to be through variables. And intensive variables, stress, electric field, and temperature, are going to be our across variables. So we're going to restate these. Remember, intensive variables. So S, which is a function of strain, which is a function of stress, electric field, and temperature. Dielectric displacement, which is also a function of stress, electric field, and temperature. And then entropy, which is a function of stress, electric field, and temperature. And then the differential form of that, as we explained in the previous slide. Now, the relationships between each domain in the electrical, we have the dielectric displacement is equal to the permittivity times the electric field. And remember that this is for the conjugate pair, so we're not considering the polarization in this case. Mechanical, stress is equal to a stiffness times a strain, or the strain is equal to a compliance times the stress. And in the thermal, the change in the entropy is equal to the density, this term, which is density times the specific heat capacity divided by the temperature, that term multiplied by the change in the temperature, delta theta. So in the electrical domain, we know that it's orientation dependent. So dielectric displacement is going to be computed from this tensor matrix of the permittivities depending on the direction, and then we come up with a general expression di is equal to the permittivity ij from the tensor multiplied by the electric field depending on the direction. Also, the stress and strain are orientation dependent, so we also have to put those into a matrix format. And then we have to make a short notation to try to simplify these things. And this is basically, you can go through this on your own. It's very straightforward. Because the tensor had xx, yy, zz, then we make these terms consist of just x, y, and z. And then yz, xz, xy, these cross terms then are given t4, t5, and t6 to try to simplify our notation. And then we get a new strain-stress relationship. Now, for a mechanical material where we're dealing with stress or strain, we have 6 degrees of freedom. Okay, so we have to be a little careful on how we formulate this. And essentially what we do is we give an example of a stiffness matrix. It gives a strain with respect to the stress, and then the 6 degrees of freedom. And depending on the type of material, these coefficients will be given certain numbers. So this is an example for silicon dioxide, and on the right, this is for silicon. So all other terms for silicon, other than S11, S44, and S12, are going to be 0. So it's a very crystalline material in a particular direction. So then the relationships across the domains. This is our example. So we have strain, dielectric displacement, and then the change in the entropy is equal to a function of the stress, electric field, and change in the temperature. So then SD and delta sigma are functions of these three variables. And then we use from thermodynamics the extensive internal energy change, as we defined earlier, or the intensive change in internal energy, as derived before. So then if we combine these two, we have S, D, and delta sigma is equal to these three equations. Then we can expand this using our internal energy. S is equal to a small parameter S, E theta, times temperature change, plus D theta E, plus alpha E delta theta. And we could do the same thing with the dielectric displacement, and we get a series of three terms with these leading coefficients, and then also the change in entropy. Now each one of these leading terms has a particular effect. You can see that the SE theta is elasticity, D theta is the converse piezoelectricity, alpha E is thermal expansion, which is in the red box, and you can go through, and each one of these terms has a particular physical effect. So that's how we translate, using thermodynamics, between a coupled domain. Okay, now we're going to apply this to a two-port network model. First, we'll go through understanding how to analyze the two-port network model, where we have effort and flow, and how that's related to the input and output of the sensor. This is the domain-independent description, and the domain is specified by the variables E and F. The general description does not have a detailed structure of the internal components, but it can be added using our previous knowledge, using thermodynamics. At each of the signal ports, two variables are defined, across E and through variables F. Each domain, the variables E and F are defined such that their product equals energy density type. And these are examples of mechanical, pneumatic, hydraulic, electrical, magnetic, and thermal, and the associated cross variables in unit, and the through variables in unit. So what do? We have a two-port network with our cross and flow variables, and we define EI is equal to some function of Fi and Fo, and Eout is also a function of Fi and Fo. We do a Taylor series expansion of DEI, and a Taylor series expansion of DE0. You see in the two equations in the middle right of the slide. And then we can reformulate this into EI is equal to alpha Fi plus gamma Fo. Eout is equal to gamma times Fi plus beta Fo. And then we can put this into this matrix format, where the vector components EI, Eout is equal to this component matrix, 2, multiplied by our through variables, Fi and Fo. An example of an electrical system using the same configuration. Our cross variables, of course, are voltage, and our through variables are current. Using the same procedure, then we know that VI, V1, and V2 are related to current I1 and I2 through impedances Z11, Z12, Z12, Z22. We know the input impedance, If we want to determine the coupling coefficient between these, then we use this general method where we open the output, set I2 equal to 0, and then we solve for this impedance ZIO is equal to Z11. Then we short the output, we make V2 equal to 0, and then we get this ZI short equal to this expression of the impedances. Another way to do this is we look at the output impedance. We open the input, make I1 equal to 0, and then ZOO is equal to Z22, or we short the input impedance, V1 equal to 0, and ZOS is equal to Z22 times 1 minus Z1 squared over Z11 over Z22. In this case, the coupling coefficient in the system, K squared, is equal to Z12 squared over Z1 Z22. This is the coupling coefficient between the two systems. In the general case, you can use these two methods, using the input impedance or the output impedance to determine the coupling coefficient, and you get the same result in the end, that the coupling coefficient in this case, K squared, is equal to alpha squared divided by 8, gamma squared divided by alpha beta. If we go back to our piezoelectric system, and you will have to do some of these examples on your own to make sure that these equations make sense. So we have the strain is equal to an equation F3, F4, F3 as a function of stress, and we got rid of temperature in this case, stress and electric field, and dielectric displacement is equal to a function F4, which is a function of stress and electric field. Then we can expand this based on our previous derivation. So S is equal to SET plus D times the electric field E. Dielectric displacement now is D times the stress plus this epsilon T times the electric field, putting this into matrix format. Then we see D is our piezoelectric charge constant, SE is compliance at a shorted output, and epsilon T is its dielectric constant at an open mechanical output, T equals 0. So we're really combining the general form of the two-port network model with our thermodynamic derivation of the system variables. In this case, remember that we left out temperature and entropy, just to simplify the system, but it could be included. Then our output becomes a bit more complicated in our interpretation of the system. Then in this case, our coupling coefficient, kappa square, will be equal to D square. In this case, this should be kappa square on the piezoelectric coupling constant, divided by SE epsilon T. So the consequences of this: stiffness depends on electrical load, dielectric constant depends on mechanical load. If that's not clear to you, please send me an email. But the general concept of what this coupling coefficient means, this is really coupling of the two domains. We can also do this using the strain and the electric field, and these are functions of the stress and the dielectric displacement, and then we get a different set of equations, and in this case the strain is equal to ST times stress plus G dielectric displacement, and the electric field is a combination of this minus G times the stress plus 1 over epsilon T times the dielectric displacement. In this case, G is a piezoelectric voltage constant, and SD is a compliance at an open electrical output. Dielectric displacement is equal to 0. So we can derive the properties of this as well, and we see that our piezoelectric coupling coefficient kappa square now is G squared times epsilon T divided by SD. Consequences. Stiffness depends on electrical load. Dielectric constant depends on mechanical load. So remember that all of these piezoelectric parameters are orientation dependent. So it was a bit complicated. So the dielectric displacement is equal to d times t and epsilon t times E. And all of these different terms are orientation dependent, and we made many simplifications. Now, epsilon ij is a 3 by 3 permittivity matrix. It had 9 elements. This is called a tensor. And also the piezoelectricity matrix had 18 elements. Okay, and so it was a bit complicated. So what I recommend is the lecture was quite long today. I recommend to go through the parts thermodynamics and the two-port network model and understand how to derive the coupling coefficient for the two-port network model. That's the most important part of this. And try to understand the fact that we were trying to do two things. We were trying to describe this physical coupling of energies and then apply it using a two-port network model that can be very general or it can be very specific depending on how you apply thermodynamics to your system. If you have any questions about the material in the lecture today, please send me an email and I will get back to you with a response within 1 or 2 days so we can sort out any difficulty in some of the material that you probably haven't had prior. That is the end of the lecture today. Thank you. The appendix is located on the remainder of the slides that follow.